Hello dear students, myself Bhagyashree Vijay Rathod from ENTC department, Modern College of Engineering. Today we'll be discussing about digital electronic. So the contents which we cover today will be introduction to digital electronic, then logic gates, next classification of digital electronics. In classification, we'll first study combinational circuit. In combinational circuit, we'll be studying half adder and full adder, and next is we'll just see the introduction of a second digital electronic circuit, which is an sequential circuit. So digital electronic and logic design are the key concept in both electronics and computer science. Digital systems are at the core of everything from basic devices like calculators, computers, our CPUs, desktop, mobile phones, everything. Okay, so digital system use binary numbers, zeros and ones to represent and process information. The digital electronic circuits, these circuits are made up of tiny electronic components which are called as an logic gate. Okay, so logic gate, what are they? They are electronic circuits that can perform Boolean or logical function on input signals. Okay, and the main component of logic gate is transistor, which act as an switching device. That is, it will either turn on or off, and in digital electronic we use zeros and ones. So 1 is what? When our transistor is turned on, and 0 stands for open circuit, that is our output will be 0. Okay, so logic gates, there are different type of logic gates. The basic gates are AND, OR and NOT. Okay, and universal gate, that they are NAND and NOR gate. There are other different gates also. So the circuit which you can see on the screen is just in simple circuit which comes under combinational circuit. Okay, it consists of an AND gate or NOT gate. Okay, so next is, and one more thing, before designing or constructing a digital electronic circuit, a designer or an engineer try to minimize the logic redundancy. That is, so the circuit can become simpler, which uses less components and become cost effective. This also reduces the chance of error in design and construction of digital circuit. To reduce the logic redundancy, there are various techniques in digital electronics such as Boolean algebra, K-map, Cohen-Mikulski method. These all are the types which reduces the logic redundancy, which makes the circuit more simpler and also makes easier for us to evaluate it. Okay, so now there are different number systems in our logic design, but now in this video we'll basically focus on the binary number system. Actually there are basically four type of number system. First is binary number system. Okay, which is whose base is 2. Next is octal number system, whose base is 8. Third is decimal number system, whose base is 10, and fourth one is hexadecimal, whose base is 16. So as you go forward in this subject, you will come to know that how these number systems are used. In this video we'll basically focus on binary number system. Okay, so this is a number system with base, or it is also called as an radix point. 2 is known as an the system which uses base 2 is known as an binary number system. Okay, so there are only two symbols are used in this number system, that is zeros and ones. So the number system whose base is 2 and act as the foundational concept in digital electronic. It is also used for representing informations in digital format as shown. So this is just a simple example I have given here, which cycle which consists of an 0 and 1 only. The data is 0 1 0 1 0 1. It can be 0 0 1 1 and so on. Okay, so the leftmost bit is known as the most significant bit, that is this one. Okay, this 0 is the MSB bit, which is a most significant bit, and the rightmost bit is known as an least significant bit, which is also denoted as LSB. Okay. And in this binary number system, the group of 4 bit is known as nibble, and a group of 8 bit is known as an byte. Bit means what? Now if I have an example like my binary number are 1011, so this number 1011 consists of 4 bits, so it will be called as an nibble. And if I have 10110011, now how many bits I took? 8 bits. So it will be called as an byte. That is 1 byte. 1 byte consists of an 8 bit of data. Okay. Yeah. So next we'll move towards the different techniques used in digital electronic for different concepts. Now we'll basically focus on binary arithmetic, how the addition is done uh, with the use of zeros and ones. So what is in binary arithmetic? It is a mathematical method of performing arithmetic operations like addition, subtraction, multiplication, division on binary numbers. It is a foundation of data processing in digital electronic. These so first is how we'll add two zeros. 0 plus 0 is of course 0. 0 plus 1 will be 1. 1 plus 0 will be 1. And 1 plus 1 will not be 2. Why? Because we are studying digital electronics. That is basically we are studying binary numbers. So binary numbers we play in 1 and zeros only. There will be no decimal numbers. So 1 plus 1 will is 0. So the answer, that is the carry, will be 1. Okay. Yeah. So our next topic is logic gates. So in digital electronic, logic gates play a very important role. Okay. So what are they? Logic gates are the building blocks of any digital system. It is an electronic circuit having one or more than one input and only one output. The inputs can vary. There can be number of inputs to our gate, but the output will be one. Okay. So, which are they? The most common gate, which are called as an basic logic gate, are AND, OR, and NOT. And the universal gates are two, that is NAND and NOR. And XOR and XNOR gate are also there. Okay. Now, we'll see the symbol. These are the symbols of our gates. And gates, AND gate is this is a NAND gate. This bubble is also an inverter, that is. And NAND gate, how it is implemented, it is the complement of AND gate. Why? Because we are at the output of AND gate, we are inserting a bubble, that is this NAND gate ka output will be inverted output of an AND gate. Okay, both are opposite to each other. Okay, so whatever will be the output of AND gate will be complemented, and that complemented output will be called as a NAND gate output. That is, this is AND gate only, but we are inserting a bubble over here. That is, we are inverting the output, so it is called as a NAND gate. Okay, next basic gate is our OR gate. Okay. And next is NOR. Similarly, we have to here a bubble is inserted, so it is called as a NOR gate. This is a basic gate, which is a NOT gate. Next are XOR and XNOR. These are the symbols. Now we'll see in short this the operation of our logic gates. So first one is our AND operation. So this is my AND gate. Here I have shown two inputs A and B. We have one output, and the equation of AND gate is A multiplied by B. And how will be its truth table? This is our truth table. You must have already known all these gates. I'll just take a quick revision of it. So my equation is A multiplied by B. So how you'll calculate or how you'll find out the truth table? A is 0, B is 0. 0 multiplied by 0 is 0. Next is 0 and 1. 0 ones are 0, 1 zeros are 0, and 1 1 is 1. So this is the truth table of your AND gate. Next is OR gate. OR is what? A plus B. So you'll add both the numbers. Okay, so 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 1. We have studied in addition, 1 plus 1 is sum is 0 and carry is 1, but here we have a table, so here you have to consider it as an 1, that is an carry gate. Okay, next is our inverted gate, which is also called as an inverter or a NOT gate, or it is also called as an complementation. Okay, so how you'll read it? Y equals not of A. Our equation is y is equal to A bar, that is what will if I have a input over here 1, the output will be 0. Okay, that is y equals complement of A. And if my input is 1, output is 0, input is 0, output is 1. And this round is called as an bubble. Okay, next is our NAND gate. As I explained earlier, NAND is what? It is then complement of AND gate. Okay, so the output will be A multiplied by B, complement of it. So 0 0 is 0 zeros are 0, complement of 0 is 1, so output will be 1. 0 ones are 0, complement 1. 1 zeros are 0, complement 1. Okay, and 1 1 is 1, complement is 0. Okay, so similarly further gate will work. Next is our XOR, complement of OR gate, and the last one is sorry, this I have mistaken, this is a NOR gate, which is complement of OR gate. Okay, and last is XOR gate. So XOR gate, the equation is A XOR B. How you'll expand how this equation came from here, the first equation will be y is equal to A bar B plus A B bar. By reducing it, it will be A XOR B. Now how the circuit, this XOR gate, the application is where the circuit finds two digital signals are to, when the two digital signals are to be compared, this gate is used. How you will explain it? When both the inputs are same, okay, 0 and 0. Okay, when both the inputs are same, output is 0, and when the both input are different, output is 1. So the circuit finds application where two digital signals are to be compared. Next is classification of our digital electronic circuit. So basically there are two type of circuits used in digital electronics. First is a combinational circuit and next is an sequential circuit. We'll study both of them one by one. Next is first we'll study a combinational circuit. It is a circuit in which different type of logic gates are combined to recognize as a combinational logic circuit. Okay, so these are the type of digital logic circuit whose output is solely a function of the current input. That is, the output depends only on the current input. They do not have a memory element, meaning their output does not depend on the past input or any state. These circuits are built using logic gates such as AND, OR, NOT, NAND, NOR, XOR and XNOR. That is, we can use any logic gate to implement any combinational circuit. Okay, so there are different type of combinational logic circuit such as adder, subtractor, decoder, encoder, multiplexer, demultiplexer, and there are many more. So in this lecture basically we will cover adders, that is we'll study full adder and then half adder. This is the basic block diagram where we have an n number of input and we can have an m number of output. So first is an adder. A digital circuit designed to perform addition of two numbers are called as an adder. Adders are widely used in arithmetic logic units and calculators. There are two types of adders, namely half adder and an full adder. Half adder is an adder circuit that can add only two binary digits and produce a sum and an carry output, while a full adder is one that can add three binary digits. So we can see over here from the block diagram, we can make out that a full adder has three inputs A, B and C in, and two outputs carry and sum and carry. Okay, and half adder has two inputs A and B, output sum and carry. This I am just giving the rough review since we are studying a block diagram on this slide. So I have just given some basic points to remember what is the difference between both, how many number of input and output are there. We'll study now in detail about the half adder. What is it? As we studied in earlier slide, there are two inputs and two outputs. So a half adder is an arithmetic circuit that needs two binary inputs and two binary output to perform the addition of two single bits. Okay. So here we have an truth table. Now we have two number of inputs. So the combination will be 4. Okay. 2 raised to n. So 4 combination. Now A first is 0 0. So my 0 plus 0 since we have two in output sum and carry, we will draw a 2k column. This is an output column, this is an input column. 0 plus 0 is 0, so sum 0 carry 0. 0 plus 1 is 1, so sum 1 carry 0. 1 plus 0 is 1 carry 0, and 1 plus 1 is sum 0 and carry 1. Okay, now we'll find out the equation. This equation is found out with the help of this K-map. You already I am considering that you already know the K-map, because if you are studying half adder, we have already covered a K-map and all, so there is no need to explain in detail, but I will take a rough review. So how you will draw a K-map? Now I have a 4 combination and 2 inputs. Okay, so my K-map will consider 4 cells having 2 inputs. Okay, so the equation which we get from this K-map is A XOR B, and from the second column, that is carry, 0 0 0 1, output is 0 0 0 1. So depending upon that truth table output, we'll draw K-map where the equation which we get is A multiplied by B. Okay, so by reducing it, what we'll do is we'll draw a circuit, combinational circuit. So how it will be? Our sum equation is A bar B plus A B bar, which is nothing but A XOR B. So no need of drawing A bar, that is giving a NOT gate over here, then multiplying it with B bar, then you will draw a AND gate, then you will draw further, you will give it to OR gate, that is addition is OR gate, multiplication is AND gate. So no need to draw such type of combinational circuit. You have already provisioned to shorten it. So we'll use directly an XOR gate. Okay, by reducing this equation. So single XOR gate will do our work. Next is carry weight. So C is what? A multiplied by B. So this is my AND gate, multiplication gate. A multiplied by B. Okay, fine. So yes, in exam there can be a question that is implement an half adder using NAND gate, or it can also be asked like implement an half adder using NOR gate. So this is a NAND gate implementation. How it is implemented? Actually, I have not written over here the outputs, but you can draw it in your notebook and find out. Now my sum equation was what? A XOR B. Okay, so the output over here should be A XOR B. Now I have this gate. This is my A input. Where it is going? It is going over here. Okay, and this gate is having two inputs. First input is A. Second input is coming from the output of first gate. Okay, so the input of this gate will be what? A multiplied by what will be the output of this gate which is going over here? It will be A multiplied by B the whole bar, because it is what? It is coming out of NAND gate. Okay, so the processing which will be going in this gate will be A multiplied by A bar plus A multiplied by B bar. Okay, and what will be the main output over here? A multiplied by A bar is what? 0. what is remaining is A B bar. So here the output will be A B bar, and here it will be A bar B. You can draw it in your notebook and just find out. Your output will be A bar B, and here it will be A B bar, and which will give further the sum equation, that is A XOR B, and carry is A multiplied by B. Similarly, the way how we calculated in the this part, you have to calculate in this part also. Okay, next is half adder implementation using NOR gate. Actually, this question is very important. Always you'll get an question ki no draw or implement an half adder using NAND or NOR gate. So this is important. Next is our full adder. So what are they? Half adder can be used to add two numbers only. To overcome this issue, the full adder was designed. Okay, the full adder is employed to add three 1-bit binary numbers A, B, and C in, and generate the output as sum and carry. This is the block diagram of it. And next comes our truth table. In truth table, we have columns of input and output. Output is sum and carry, and input are three, so it will be A, B, and C in. Okay, number of combinations will be 0 to 7. Okay, that is there will be 8 number of combinations. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, so how you'll do the calculation? See, we have to add these three numbers. Okay, so 0 plus 0 is 0. The output of these two will be added in this one, third one. Okay, so 0 plus 0 is 0, 0 plus 0 is 0. Sum 0, carry 0. 0 plus 1, 0 plus 0 is 0, 0 plus 1 is 1. So sum 1, carry 0. 0 plus 1 is 1, 1 plus 0 is 1. So sum 1, carry 0. Now here 0 plus 1 is 1, 1 plus 1 is sum 0, carry 1. We have already seen arithmetic operation. Okay. Now let's see this last condition, which is 1 plus 1. What it will be? Sum 0, carry 1. Okay. Next, again 0 plus 1, 1. So here will at both the columns at sum will get 1 and carry also will get 1 output. Okay. Now with the help of K-map we have found out the equation of sum and carry. This is the logical expression of sum. Now I'll explain you first. First term is what? Sum is, here they have written A bar, B bar, C in. How you found out that? A bar, B bar, C in. Okay, in K-map what we do is we make group of ones varying from 1 to 4 8. Okay, we have to do big, as much as big group is there, your equation will get reduced, but here there are no such, it is not possible over here to do group of 2 or 4 or 8. Okay, so we have to take single terms only. Okay, so this one, its term is A bar, B bar, C in. For this one, our term will be A bar, B, C in bar. For this one, A, B bar, C in bar. For this one, A, B, C in. Okay, so here they have written the same. By reducing it, we'll get an expression as A XOR B XOR C in. Similarly, we'll go for C in. Here, what are we doing? We are making group of 2. So this is my first group, this is my second group, and this was single. So instead of taking it single, the terms will increase, right? So what we did is we combined these two. Okay. So these are our equation for an sum and carry of full adder. And this is our circuit, combinational circuit, where what are we doing is we are adding two half adders. This question is also important. Implement a full adder using two half adders. Okay. What is the main difference between a half adder and a full adder? Is that full adder has 3 input and 2 output. On other hand, a half adder has only 2 input and 2 output. Similar to the half adder, a full adder can also be realized using universal gate, that is NAND and NOR gate. Next type of circuit is an sequential circuit. Now we studied combinational circuit. Okay, combinational circuit, what it is, the output doesn't depend upon the previous input. Okay, so they are independent. As input changes, output changes in this way. But in sequential circuit, what happens is, sequential circuits have memory elements, meaning their output depends not only on the current input but also on the sequence of past input. This memory capability allows them to store information and perform more complex operations such as counting, storing data, and generating sequences. What are the features? It contains memory element, it is state dependent, clock operation is there for synchronizing, and complex function, that is enables counting, data storage, and sequencing. So if you see the block diagram of it, a sequential circuit is a combination of combinational circuit and a memory element. Your memory element which we use are called as a flip-flop. Okay, so flip-flop contain 1 bit of memory, so only 1 bit can be stored in it. Okay, further you'll see in detail what do you mean by flip-flop and what are the types of flip-flops, how they work and all. But the basic block diagram, we have a combinational circuit and then memory element. Now this combinational circuit is getting one input, okay, and the second input which is coming from which side, the output side, is given as an feedback. Okay, this is called as a feedback, which is stored in the memory, and that data is given to the input of an combinational circuit. That is, second input of our combinational circuit is what? It is nothing but an output which is given as an feedback through the memory element. Okay, so what we can make out from this, that the output depends on the feedback which we give, that is, it depends on the previous output. Okay. Now, how they are classified? They are classified in two types: synchronous system and asynchronous system. What are they? Those sequential circuit that use a clock signal for triggering the change in their state are called synchronous system. And asynchronous system, a system that do not use any clock signal and change their state according to applied input, are called as asynchronous system. So sequential circuits are of two types, synchronous and asynchronous. Depending upon the clock signal, you can uh, differentiate between them. I'll give just a rough review of a clock signal. What it is? It is a series of pulse basically, where the signal alternates between zeros or one, that is high and low. Ideally, a clock signal will look like a square wave, as you can see in this waveform. So this is my low level, this is my high level. Okay, and one clock signal is this much, that is one cycle. So this is my rising edge from where the clock starts, and this is my falling edge. This side is my falling edge. Okay, and the one clock cycle is from here to here, the way we see the sine wave. Okay, this is a one cycle of our clock signal. Thank you so much.